Our first objective for lesson 20 is for us to be able to apply the rational zeros theorem. And the rational zeros theorem is a theorem that tells us if we're looking at a polynomial, it tells us how to form a list of all of the possible rational zeros. Really quickly, rational numbers are numbers like 1, 2, -3, 4/7, 5/3. All of these are examples of numbers that are rational numbers. Rational numbers are an integer divided by another integer. Things that are not rational numbers are things like the square root of 3, 4 minus the square root of 5, and 4 plus the square root of 5, 2 minus 3i, 2 plus 3i. These are not rational numbers. These are either irrational numbers or imaginary numbers. So what this theorem is going to do is it's going to help us form a complete list of all of the possible rational zeros of this polynomial. To form this list, we first begin by listing factors of the constant term. In this case, our constant term is -15. That's the term that has no x. Numbers that multiply to give us 15, factors of 15, are 1 and 15. So I'll put plus or minus 1 and plus or minus 15, because if 1 and 15 work, then -1 and -15 also work. Moving on to the next pair, 3 and 5 are also numbers that multiply together to give me 15. And there are no more numbers. So those are all of the 8 different factors of 15. Next, I'm going to list factors of our leading coefficient of this polynomial, which is 4. So I looked at the constant term and I looked at the leading coefficient. The numbers that multiply to give me 4 are plus or minus 1 and plus or minus 4. And that list also includes plus or minus 2. Now that we have these two lists of factors of our constant term and of our leading coefficient, we are now able to write a list of all of the possible rational zeros. And we form this list by taking a number in the first list and dividing it by a number in the second list. So for example, if I were to take 1 and divide it by 1, I would get plus or minus 1. If I were to take 1 and divide it by 4, I would get plus or minus 1/4. And if I were to take 1 and divide it by 2, I would get a positive 1/2 and a negative 1/2. And now we'll do the same thing by moving on to the second number in the first list. We'll take the 15, divide it by 1, divide it by 4, and divide it by 2, which gives us plus or minus 15, plus or minus 15/2, and plus or minus 15/4. Moving on to the third number in the first list, 3, we'll take that 3, divide it by 1, divide it by 4, and divide it by 2, giving us plus or minus 3, plus or minus 3/4, and plus or minus 3/2. And then finally, I'll take the 5 and divide it by 1 to get plus or minus 5, divide the 5 by 4 to get plus or minus 5/4, and then take the 5 and divide it by 2 to get plus or minus 5/2. Now this is the list of all of the possible rational zeros of this polynomial. One thing that is clear is that it's not possible that all of these numbers are zeros for the polynomial, because this polynomial can have a maximum of 3 zeros, because the degree of that polynomial is 3. So it cannot have more than 3 zeros. It's also possible that not all of the zeros for that polynomial are rational. It could have irrational zeros, and it could also have imaginary zeros. But this is the list of all possible rational zeros. Us to go a step further, we're not just being asked to find all the possible rational zeros. This time we're actually being asked to find the zeros and the multiplicities of those zeros. So we're going to start off the same way. We're going to begin by first writing the factors of our the factors of our constant term, which in this case is 3. And the factors of 3 are 1 and 3, and I'll make sure to put plus or minuses in front of both of them. Then I'm going on to list the factors of my leading coefficient. The leading coefficient in this case is 2. The factors of 2 are plus or minus 1 and plus or minus 2. Now that we have those two lists formed, we are ready to write our list of possible rational zeros. I'll begin by taking the 1 and dividing it by 1 and dividing it by 2 to give me plus or minus 1 and plus or minus 1/2. Then I'll take the 3 and divide it by 1 to give me plus or minus 3, and the 3 divided by 2 gives me plus or minus 3 over 2. So now that we have these lists of possible rational zeros, what we will need to do is we will need to test these numbers to see which of them are actual rational zeros. And to test these numbers, what I'm going to do is I'm going to create a table, and I'm going to plug all of these x values into this function. So basically I want to know what is f of 1, what is f of negative 1, what is f of 1/2, what is f of negative 1/2, and I'm listing the numbers that are in this list here. And the ones that give me out 0 are the ones that we will use as our zeros. So it's going to be very time consuming to test all 8 of those numbers individually, and so I'm going to do it using my calculator. Well, if we were in class, we would do it using a calculator. I'm going to show you how to do it using a table on Desmos because you don't get to take our calculators home. And so you still need a way to do this when you are at home. Opened up Desmos. I'm going to click on this plus sign to add a table in. I'm going to just simplify this left column and just make it x. And then what I want to plug into is the function 2x to the 4th. Plus x to the 3rd minus 5x squared minus x plus 3. That's just our function that we were working with from example 2. And then the numbers that we want to plug in are the numbers in our list of possible rational zeros. So those numbers are 1, negative 1, 1/2, negative 1/2, 3, negative 3, 3/2, and negative 3/2. Okay, so I have all of these numbers plugged into this list, and now we can see which numbers give us 0 and which do not, because the ones that give us 0 are going to be our actual rational zeros for this polynomial function. So I'll just move this table in here, and let's go take a look at this. So we can see that when we plugged in 1, we got out 0. When we plugged in negative 1, we got out 0. And when we plugged in a negative 3/2, we got out 0. So this function has 3 zeros. It has a 0 of 1, it has a 0 of negative 1, and it has a 0 of negative 3/2. And we're also being asked to find the multiplicities for these zeros. So I'll go ahead and list my zeros in this table of 1, negative 1, and negative 3/2. Now, before we figure out what the multiplicities are, what we definitely know is that one of those zeros has to show up with multiplicity 2. And we know that because the degree of this polynomial is 4. So if we have a 4th degree polynomial with 3 zeros, one of these zeros has to be repeated to give us that total degree of 4. And to figure out which zero is repeated, we can go and we can look at the graph of this polynomial. Because if I were to graph this polynomial, which I'm just going to enter this into this y equals here on Desmos, what we would see is that one of these zeros would be touching the x-axis. So we can definitely see the 0 at 1 is touching. At negative 1, we're crossing through the x-axis, and at negative 1.5, we're also crossing through the x-axis. And what we learned in a previous lesson is that if a 0 is only touching the x-axis, it has even multiplicity. So 1 must have multiplicity 2, because the graph is touching the x-axis at 1. So the multiplicity of the 0, 1 is 2, and I know that because here this is touching, so I know that it has even multiplicity. And you may wonder, well, how come it couldn't have multiplicity 4 or 6 or 8? Well, remember, the degree of this polynomial is 4. So all of these total multiplicities have to add up to the degree of 4. And the negative 1 and the negative 3/2 are simply left with multiplicity 1. We know that they're crossing, and again, these multiplicities have to add up to the degree. We weren't asked to do that in example 2, but I do want to mention from these zeros, we can then build factors, because if 1 is a 0, then x minus 1 had to be a factor. If negative 1 is a 0, then x plus 1 had to be a factor. And if negative 3 halves is a 0, then 2x plus 3 had to be a factor. And because 1 had multiplicity 2, this x minus 1 right here should be squared. And so this is how that entire polynomial would factor. We were being asked to find all the zeros and to factor the polynomial completely. I'll begin by listing my factors or divisors of my constant term, which is negative 24. The leading coefficient in this case is 1, and so I don't really have to list those divisors of 1 because the only numbers that divide 1 are positive and negative 1. And then when I formed my list of possible rational zeros, it would be the exact same list as the divisors of negative 24, because we would just take all those numbers and divide them by 1. So I've gone back to Desmos. I'm going to go back to my table, and I'm going to, again, just change this to x. I'll change this second column to be our polynomial. And now I'm going to start typing in the numbers that we have for our possible rational zeros and making a note of which ones actually give me 0. So I try 1, negative 1, 24, negative 24, 2, negative 2. So negative 2 is giving me 0, so that number I will add to my list of actual zeros. 12, negative 12. 3 has given me 0, and I can see that negative 4 has also given me 0. And at this point, I can stop looking for zeros because the degree of our polynomial is 3. And so there can be no more than 3 zeros. So we have found the zeros for this polynomial, and now we're ready to write the polynomial completely factored. Generally speaking, if you have the number a as a 0, then x minus a is a factor. So if negative 2 is a 0, x minus negative 2, which would be x plus 2, is a factor. If 3 is a 0, x minus 3 is a factor, and if negative 4 is a 0, x minus negative 4, which is x plus 4, is a factor. So now we have written the polynomial completely factored. In example 4, I'm going to begin by first finding a list of possible rational zeros. To do that, I'll need to list divisors of 30, and then I'll also need to list divisors of 2. I always recommend you start by listing divisors of the constant term first, because those are the ones that are going to be going into the numerators when you form your list of possible rational zeros. So I've listed all of the divisors of 30, just thinking about pairs of numbers that multiply to 30. The divisors of 2 is a much shorter list. There's only 1 and 2 in that list. Do make sure you put plus or minus in front of all of those numbers. And now I'm ready to form my list of possible rational zeros by taking a number in the first list and dividing it by a number in the second list. 30 over 1 is 30. 30 over 2 is 15. 2 over 1 is 2. 2 over 2 is just 1, so I don't have to repeat that. Now I'm on to the 15. I'll take 15 and divide it by 1 to get plus or minus 15. Then I'll take 15 and divide it by 2 to get plus or minus 15 over 2. 3 over 1 is 3. 3 over 2. 10 over 1 is 10. 10 over 2 is 5. 5 over 1 is 5, which I don't have to repeat. So we did the 10 over the 1 to get 10, and then we did 10 over the 2 to get 5. But then when we go to do the 5 over the 1, we don't have to repeat the 5. But I will put down that 5 over the 2 is 5 over 2. And the last thing we have is the 6, which will give us a plus or minus 6 and a plus or minus 3, but that's already in our list, and so I don't need to repeat that again. So I went ahead and put our equation into this table on Desmos. We have a lot of different x values we need to check here, but if you're using Desmos at home to work on assignments, or if you're in class and you're using your graphing calculator, once you have this on your paper and you know your possible rational zeros, nothing stops you from just looking at the graph and then picking up what the actual zeros are, because the zeros are going to be where the graph is either touching or crossing the x-axis. So just from looking at that graph, I can see that the actual zeros of this polynomial are at -5, -3, 1/2, and 2. So now that we know the zeros of the polynomial, let's write the polynomial completely factored. There's a couple different ways that we can do this. If -5 is a zero, then x plus 5 is a factor. If -3 is a zero, then x plus 3 is a factor. If 1/2 is a zero, one way you could write that is that x minus 1/2 is a factor. I'll have to come back and mention something about that. And if 2 is a zero, you can put x minus 2 as a factor. Now, the problem with writing x minus 1/2 is that if you pay attention to the leading coefficient here, multiplying x by x by x by x is going to give us an x to the fourth, when we should have a 2x to the fourth. So if you choose to write x minus 1/2, you have to put a leading coefficient of 2 in the front to handle that fraction. The alternative is that you write, these are the first two factors from the first two zeros, but instead of x minus 1/2, you could write 2x minus 1. And that takes care of the leading coefficient being the problem, and it still maintains 1/2 as a zero. Similar thing in example 5, we want to find all the zeros and factor the polynomial completely. I'll begin by listing divisors of the constant term -91. 1 and 91 is a pair, and then 7 and 13 is another pair. From that, I don't necessarily have to look at the divisors of 1, which is what the leading coefficient is right there, because that's just plus or minus 1. And from those two lists, I will form my list of possible rational zeros. And because I'm just going to be taking numbers in the first list and dividing them by 1, this list is exactly the same as that list. So now that we know all of the possible rational zeros, I can now head over to my calculator to figure out which of these are actual rational zeros. And so to do that, I have started creating a table on Desmos. And in this table, I will plug in 1, -1, 91, -91, 7, -7, 13, and -13. So when I do that, I can see that I do have an actual zero at 7. And I can see that also here on the graph. If we had looked at the graph of this polynomial, we would have quickly saw that the only zero, not even the only rational zero, the only real zero that that polynomial has is 7. So we do know that technically, though, two things are missing, because the degree of this polynomial is 3. If we had found all of the zeros, we would have been able to write all of the factors. We would have known that g of x, which is equal to x cubed minus 13x squared plus 55x minus 91, is equal to, one thing we do definitely know is that because 7 is a zero, x minus 7 is a factor. But there's factors that are missing here that we don't know. And we do know that what's missing has degree 2. It is a quadratic factor. I know it has degree 2 because the total degree should add up to be 3. So the two zeros that we are missing are from that quadratic piece. So we need to find that quadratic piece, and then we can go on to find its zeros. So to solve for this missing quadratic, I'm going to come into this equation and I'm going to divide both sides of this equation by x minus 7. So that this will cancel here. So now we need to perform that division, and I'm going to do this division using synthetic division. So then synthetic division tells me to take what we are dividing by, which is x minus 7, That's linear in this case. Set it equal to 0 and get that x is equal to 7. That 7 number goes in the box. I'll line up the coefficients of the dividend. The number in front of x cubed is 1. The number in front of x squared is negative 13. The number in front of x is 55. And the number with no x is a negative 91. Going through this division, we should get a remainder of 0. Good, because it is a factor. And now we can see that the missing quadratic is 1x squared minus 6x plus 13. So now I can go a step further to say that I know that g of x is equal to x minus 7 times x squared minus 6x plus 13. And the last two zeros that we need will come from that piece. And on that piece, we can now go in and do the quadratic formula to find our last two zeros that are imaginary. And I know they're imaginary because I've seen the graph, and I've seen that that graph only had one x-intercept. So now I'll plug all this into the quadratic formula. So I'm left with a positive 6 plus or minus the square root of negative 16 over 2. The square root of negative 16 simplifies to 4i. And when I divide all that by 2, I'm left with 3 plus or minus 2i. So now at this point, I can say that all of the zeros of this polynomial is the real 0 of 7, the imaginary 0 of 3 plus 2i, and the imaginary 0 of 3 minus 2i. And we can also go on to say that now the polynomial completely factored is x minus 7, x minus 3 plus 2i, and x minus 3 minus 2i. You always get your factors from doing x minus your 0, even if your zeros are imaginary. I'll begin example 6 the same way we have been. We're going to start off listing the divisors of our constant term and the divisors of our leading coefficient. Again, make sure to stick to that order. The divisors of 6 are positive and negative 1 and 6, and positive and negative 2 and 3. 5 is prime, so we only have plus or minus 1 and plus or minus 5. Now I'll form my list of possible rational zeros by taking a number in the first list and dividing it by a number in the second list. So now that we have our list of possible rational zeros, I will head over to my table to plug in these x values. So I have the x value of 1, negative 1, 1/5, negative 1/5, 6 and negative 6, 6/5 and negative 6/5, which we can see that negative 6/5 does give us a 0 because we get 0 out. And the ones we have left to check, we still have about 8 numbers to check. So when I check the rest of the numbers, I don't find any more zeros for the polynomial. Nothing else gave 0 out. But when we come look at the graph here, I can see the 0 that we found of negative 6/5. That's the negative 1.2. But there are definitely 2 more zeros, these two. But the problem why these are not showing up in our list is because the 2 remaining zeros are not rational. They are irrational. And so we'll have to go through the algebra to find what those are. So what we do know so far is that W of t is equal to, because I know negative 6/5 is a 0, I know that 5t plus 6 is a factor. And we are still missing something here that is quadratic. To find out that missing quadratic, I'm going to come in and divide both sides by this 5t plus 6. And this division here, I will do long division for. I would not recommend you do synthetic division for that because although the denominator is linear, it does not have a leading coefficient of 1. So I have my long division set up. What I have to multiply 5t by in order to get 5t cubed is t squared. I'll do my multiplication. and then we will come in and subtract. The next thing that will be going on top will be a negative 4t, because if we take negative 4t and multiply it with 5t, we will get a negative 20t squared. We'll finish our subtraction. And the last thing that will go on top is a plus 1. That we know what the missing quadratic is, we can now take this quadratic and go do the quadratic formula with it to find what those last two remaining irrational zeros are. So I have 4 plus or minus the square root of 12 over 2. The square root of 12 can simplify to 2 root 3. And then all this being divided by 2 leaves me with 2 plus or minus root 3. And we can check our answer, because if we go look at our graph on Desmos, or if we were looking at a calculator, I'll cut this table off for now, but what we should see is that the x value of 2 plus the square root of 3 should be one of our x-intercepts. And we can see that it is. And we should also have 2 minus the square root of 3 as our other x-intercept, and we can see that it is. So now we know that the complete and total list for the zeros of this polynomial are negative 6/5, 2 plus the square root of 3, and 2 minus the square root of 3. And now we can also write the polynomial completely factored as 5t plus 6 multiplied by 2 minus 2 plus the square root of 3 multiplied by t minus 2 minus the square root of 3. So I'm getting these last two factors here by again just doing the variable minus the 0. So I'm just subtracting those last two irrational zeros that we found there. For our last example, number 7, we are told that 1 minus 5i is a 0 of the polynomial, and we're being asked to find the remaining zeros and factors. So what's important to know with number 7 is that imaginary and irrational zeros come in conjugate pairs. So what that means is that if 1 minus 5i is a 0, then 1 plus 5i must also be a 0. If 2 plus the square root of 3 is a 0, then 2 minus the square root of 3 is also a 0 of that polynomial. So we know they told us that 1 minus 5i is a 0, so that means that 1 plus 5i must also be a 0. And there's some other 0 that we don't know, because we can see that this polynomial has degree 3. Well, if 1 minus 5i is a 0, then x minus 1 minus 5i is a factor. And if 1 plus 5i is a 0, then x minus 1 plus 5i is also a factor. And then again, there's some factor left here that we don't know that all comes together to give us this polynomial that we started with. So what we're going to do is we're going to multiply these two out together, and then we'll come in and do division to leave us to solve for whatever is missing there. Once we find what's missing, then we'll know what the last 0 is and the last factor. So let's begin by multiplying these first two sets of parentheses here. We have to do x times x, which is x squared. X times negative 1 is negative x. And then x times 5i is a 5ix. And I'll continue multiplying this out. So I have all of this multiplied out. There should be a lot of things that come in now and cancel, like this positive 5ix and this negative 5ix. Positive 5i and negative 5i will cancel. And we're left with a minus 2x from these two here, a plus 1, and a minus 25i squared. And I squared is negative 1. So that I squared is negative 1. So this is x squared minus 2x plus 26 times whatever that missing linear factor is that we do not yet know. Find what that missing question mark is. I'm going to come into both sides of this and do some division. I'm going to set this up as a long division problem. So I'll start working through this division, and we do end up with a remainder of 0, and we can see that the last missing factor was an x minus 1. So to find the remaining zeros, well, the first remaining 0 we found very quickly after we knew that imaginary zeros come in conjugate pairs. So if 1 minus 5i was a 0, then 1 plus 5i was a 0. The last remaining 0 we can see is 1, because we see that this factor of x minus 1 is going to give us 1 as a 0. So f of x written as a product of linear factors will be the first two factors that we already knew, and the last factor that we had to find using division.